Welcome to Yang Academy, lecture number 2. Today we'll be computing the gain function of a dipole antenna. So I've already drawn this little diagram here, and what you're looking at is a small dipole of distance d. This is an oscillating current source, and r is the vector from the center of our coordinate system. We've put our origin between the two ends of this thing. And r is the vector from the origin to some point where we're going to compute our vector potential and later our fields. So we defined our coordinate axis here, and what you can imagine this to be is radiating, for example, in the direction of r. Now we're going to work this example with the assumption that r is much, much bigger than d, or the wavelength that it's radiating at. So without further ado, let's get started. We can begin by asserting the definition for the current distribution along this dipole. So this thing is going to be oscillating, as stated. And a quick reminder, if you've forgotten, the vector potential A bar prime T is there. In this particular case, our prime is pointing to some point on our magnetic object, and r is just like r over here. It's pointing to some place in space where we like to compute our vector potential. So we could put these two equations together, and doing so and solving for it will give us the explicit result for the vector potential of this example. So let's do that. So, one thing quickly to notice is that we're working in units of retarded time. Retarded time, so this becomes a function of r prime, actually still t, but retarded time takes the form of this. It's equal to t minus r prime over c. We can use the property at this point of delta Dirac functions, and let's use a different color. Delta Dirac functions have the following property. If you were to integrate them over everything, basically, with a function it's in the same integrating variable, you're really just left with the value of the function at 0. So we can apply this in this particular situation. Basically, we're able to cut out and thin this integral down to just the integral along the z direction of the dipole. So we can omit everything x and y, and we can just put everything in terms of z prime. And I'll show that here. So now I have the function of z prime and t this. We can make use of the earlier assumption that R is very, very large compared to Z. And since we're only integrating along the length of the dipole, this is going to be something like R. I went off the screen, what I've drawn here. Like R. Integrating this gives us an equation that looks like this. Now we're going to explicitly state our boundaries for integration over the current density of Z prime, dz prime Z. But we know that if we integrate that, all we're left is the magnitude of the overall current. And so, final answer in this case is so here we've derived the vector potential. Now that we've derived the vector potential, why don't we get the B field using these equations? We're going to be converting from Cartesian coordinates to polar using the set of equations on the right, and also the fact that the unit vector Z follows this relationship here. So why don't we get started? It's handy because we're only going to be left with this phi term. The remainder are 0. So if we were going to write B we're left with this. We can use a second approximation to make our lives a little bit easier. Since we know that this term will actually follow 1 over R squared, we can say that B is behaves to a good extent just like the first term. So let's solve for that explicitly. Which gives us this, and I'm just going to assert the E field. We can check, if you're not convinced, that this is true by using the relationship here. I've left this as an exercise since it's rather tedious and not very informative. Now our next step is to compute the Poynting vector. We found explicit values for the electric and magnetic fields for the dipole. So we can just use our definition for Poynting vector. And just plug and play. So why don't we just work through this? Now we're only interested in the real parts of E and B. So we've used here the identity and this value here is just equal to this term, and we just compute the cross product. Which gives us the result here. And now we found the Poynting vector. Now we're going to need the time average Poynting vector to compute the total power emission. And we'll need both of those to compute the resulting gain function. So let's do that. Let's find the average Poynting vector, and we'll integrate it over one period, over the length of the period. we'll take everything out of the integral that's essentially constant. So 2 over t squared. This comes down here. And use the identity. Two. And since we're integrating over a full period, the cosine term will just end up being 0, and we're left with this part here. So our final answer to compute the total power emitted by the antenna. I said we were going to use this value, and they relate together according to this integral. We're just going to compute this quickly. We're going to be integrating over the solid angle here. The r squared will drop out through the r term in the denominator here. So those will actually eliminate each other. But we're going to be left with a sine cubed. And actually nothing is attacking the phi, so this will just be 2 pi. You can actually take all that junk out again in front of the integral. It's all squared. And we're integrating this solid angle. So, this just ends up being 2 pi. And this is 4 over 3. So, simplifying, we get this. We computed the average Poynting vector, which gave us this. And now we know the power emitted by that antenna. We can use these two values to compute the gain function of the antenna in question. Alright, let's use green this time. So our gain looks like this. Now the resulting combination, putting this here, and the vector, Poynting vector average, here, this just ends up simplifying to 3/2 sine squared theta. And that's it. That's how you get the gain of a dipole antenna. Thank you.